Now we turn our attention to Module 9, which is titled Behavioral Modeling of Sequential Logic. What we have covered in Chapter 5, Module 5, was VHDL basics. And we didn't get into anything using a process, or a package for that matter. All we did in Chapter 5 was we looked at how an entity declares the ports, how an architecture is used for functionality, and then how to do concurrent signal assignments. In Chapter 8, we covered the rest of the functionality in VHDL, and this included the process. The reason we didn't look at the process earlier is because a process is used to model sequential logic most of the time. Even though we've seen that we can use it to model combinational logic, the process is something that makes signal assignments based upon an event, and that is usually sequential logic. Okay? In Chapter 8, we also looked at adding packages in, specifically the standard logic 1164. So that was the big one that gave us these two new data types, which were standard logic and standard U logic. Okay? But really all we did in Chapter 8 was just go over all the stuff that you can do in VHDL, but we didn't give real concrete examples. So now we're in Chapter 9, and all this chapter is about is examples of how you use VHDL to model these common sequential logic systems. Okay? So the first thing we're going to do is we're going to look at modeling sequential storage devices in VHDL. What is a sequential storage device? It is a D flip-flop. That's really the main thing that we use in digital systems. If you recall what a D flip-flop is this thing right here. So let's go to the one we're going to model, which is this guy right here. Okay? A D flip-flop is a device that will store a piece of information. It will store one bit. The bit will be held on an output which we call Q. Okay? Every time you get an event, which is called a clock, and it's only the one edge of a clock, you will update with the value of Q with whatever is sitting on the input D. That is a D flip-flop. Okay? Now, key things to this is that this little triangle looking thing right here, that means rising edge sensitive. Okay? That means rising edge sensitive. If you wanted to create a symbol for a falling edge sensitive D flip-flop, you would put a little circle right there, but we're not going to do that to begin with. Everything that we're going to do for the rest of the semester is rising edge sensitive to a clock. Okay? Now, what that means is typically a clock is going to come along and it's going to be this nice square wave, and every time you get a rising edge, it is going to update Q with D. The cool thing about that is that D, it can be moving around like crazy. And as long as it becomes stable right around the clock edge, you will be able to determine the logic that's on D and pass it to Q. And then D can go back to moving. This is how everything in a digital system that is called synchronous works. Everything is held on D flip-flops. Okay? One other key component to a D flip-flop, though, is the reset line. Because if you start up, sometimes if your clock isn't running, you'll never get like an initial value. So what you do in a digital system is you always have a master reset which sets the initial value of all your D flip-flop outputs. Okay? And almost always a reset is active low, meaning that if it's a 1, you're running. Okay? Or excuse me, if it's a 0, you are reset, and if it's a 1, you are running. Okay? So it's the opposite logic of what you would think. Did I say that right? It's an active low reset. So that means when it's low, you reset, and when it's 1, you're running. Okay? Okay, so you notice that I have the bubble right there, which indicates this. The key to this is the following. Reset is always the highest priority signal in all of your digital systems. It is asynchronous, meaning that it can occur anytime. Imagine that it's a reset button, and you come up. You don't want to press that button and then have to wait for a clock to see it. You want that reset to blow everybody away, because almost always a reset happens under two conditions. One, you're powering up for the first time, and you got to let all your transistors charge up and get ready to go, and then you reset it and you put everybody in a known state, and then you start operating based on the rising edge of the clock. The other situation where you have a reset is when something catastrophic happened. Your system crashed and you want to get back to a known state and start running again. This means that resets are asynchronous. okay? And we need to model them as such. Okay, so then at this point, what we need to do is start looking at VHDL to model this D flip-flop. Now, what we're going to do, though, is I would like to keep this over here if I can, and I want to build up the test bench for this because we know how to do test benches now, and it's so fun. Okay, so here is our D flip-flop, and here's going to be the entity definition for it. Okay, so we'll put the entity definition down here, and notice that we're going to have a clock, obviously. It's not labeled clock on the D flip-flop symbol. This little greater than symbol implies that it's a clock. So we're going to call it clock in our entity. We will have a reset line. We will have an input D and output Q. And then you get a Q bar for free. You get the negated version of the output for free. Okay, so let's go ahead and write a model for this. But before I do that, let's pretend that you are a real designer. You're going to do the test bench first. So I've already created a project. And I'm going to go ahead and say add to project, a new file, and I am going to make sure that I'm in this new directory that I created, which I am, called D flip-flop. And the first thing I'm going to do is let's call it DFF_TB. That's going to be my test bench, and then we'll go add to project, new file, and we'll call it DFF, and that's going to be my D flip-flop. Okay? So let's start by doing the test bench. We always and forever use standard logic vectors for our input ports from here on out. Standard logic or standard logic vector. Those only exist in the standard logic 1164 package. So every VHDL file that I start from here on out will have a library keyword. So I do library IEEE, and then I do use IEEE dot standard logic 1164 dot all. Okay? Now, this is going to drive into my D flip-flop. So what I'm creating right here is I'm going to create the test bench, which sits around the outside of this thing, and I want to drive in ones and zeros. So here we go. I'm going to start off by doing entity D flip-flop underscore test bench, okay, is there any ports on a test bench? No, there's not. So I do end, entity, boom. Now I'm going to do architecture. I'm going to say D flip-flop TB arc of D flip-flop TB is, I just connected my architecture to my entity. I do a begin, come down here, I do an end architecture, and at this point I have enough VHDL to save and compile to make sure that I got all my syntax right and to start warming up the compiler. Now it's saying, hey man, you got a problem.
Line 1, it's not a semicolon.
Yeah, you got to get that semicolon on there. Got to get the semicolon on there. Compile, selected, boom. We are now ready. Let us think first what we do with the test bench. The whole point of the test bench is to instantiate the DUT. So the first thing we want to do is declare this DUT as a component. So I'm going to do component keyword, and then I'm going to say I'm going to have a system called D flip-flop. It is going to have ports as follows. So it's going to have a clock. I haven't even designed this yet. But I'm going to define the port definition in my component declaration in the test bench. Now, this is going to be standard logic on the clock. I'm going to have a reset, of course. And I could have had these on the same line, but I don't know why I always put them on separate lines. And then I'm going to have my inputs, which is a D. All of these could have gone on the same line. No big deal. And then what I'm going to do is have an output, which is Q. And let's go ahead and put Q bar or Q naught on the same line. And this is going to be out, standard logic. And then I am done, and I can end my component. And now that feels good. So I'm going to go ahead and I'm going to compile that up, make sure that I didn't biff it. Life is good. In addition, as I build my test bench, you have to create the signals you're going to connect to this thing. So at this moment in time, what I need to do is I need to declare signals. So I'm going to declare keyword signal, and I'm going to declare signals that are attached to this D flip-flop. I'm going to put underscore TB after the name of these signals to let me know during simulation that these are my test bench signals. So I can do clock underscore TB, and I can make it of type standard logic. Now, you say I need them all. I could put them all on the same line. But let's do it like this just to keep it a little bit cleaner to read. I got myself a reset test bench. I got myself a D test bench. And then I'm going to have myself a Q test bench. And then how about a Q not test bench? Okay. All right, life is good. I've created some signals. I'm feeling pretty good about myself. I space my puppy out down here, my begin. I save up. I compile. Bada bing. Boom. Boom. Feeling so good. Now I begin. First step of a test bench is what? I'm going to instantiate my DUT. So I'm going to go ahead and fire this up, and I'm going to call it DUT, and we'll use the compiler to remind ourselves whether the semicolon goes here or somewhere else. So I'm going to say DFF, and then I'm going to do port map, and I'm going to use positional port mapping. You know, remember what positional port mapping is? It's where you list the connections in the order they appear on the component or the port definition. So I'm going to go clock, reset, D, Q, QN, all with the underscore TB on it. And it should wire up correctly. So I just go clock, TB. I go reset, TB. I go D. Oh, I go D, TB. I go Q, TB. And I go QN, TB. And I'm done. Done. That should instantiate that puppy and wire it up. So let's make sure that I didn't biff that. Compile selected. No biffs. Now, this is where you start thinking about how are we going to drive into this. Let's think about something. We are going to drive a clock. We're going to drive a reset. And we're going to drive a D. Clock will always be going up, down, up, down, up, down, always and forever. So it should have its own process. Reset is going to reset my system and then go high and stay there forever. So what we could do is we could start it at a 0 to keep it in reset, and then we will bring it out of reset. Except for we want to kind of do this so that we keep in our mind what's actually happening with our signals. So let's think about it like this. Okay. So here's my D flip-flop, and I'm going to make a clock, TB. And I'm going to drive it in, and I want to do this. How fast you want this thing running? Name a frequency.
100 hertz.
100 hertz. I can't even do that. I'm sorry. That's so slow, it's painful. Give me something a little faster than that.
10,000 hertz.
What's that?
10,000 hertz.
10,000 hertz? That's so slow. That's so slow. And no one talks like that. 10,000 hertz, you say 10 kilohertz. Okay? Okay. What's the speed of your computer?
4.8 gigahertz.
4.8 gigahertz. Yeah, okay, no, it's gigahertz. It is gigahertz. How about 1 gigahertz? Okay, let's round it to gigahertz. So do you remember the period of a gigahertz signal? Period of a gigahertz signal is 1 nanosecond. Okay? So that's from the falling edge to this guy right there. So that's what you have if you have a 1 gigahertz clock. So let's make the clock. Let's make the clock right now. I'm going to come down here, and I'm going to make a clock process, which I call clock proc, and I'm going to do process, and I'm not going to have a sensitivity list. Okay? So now I'm going to come along, and I'm going to say I need a clock which is going to be low for 10 nanoseconds and then high for 10 nanoseconds. Why did I say 10 nanoseconds? I said 1 nanosecond. Is that right too? That's incorrect also. How low or how long is this low? 0.5 nanoseconds. So to model that, what I do is I say clock TB gets assigned a 0, and then I'm going to wait for 0.5 nanoseconds. And then you know what I'm going to do? I'm going to put this puppy high. Boom, boom. And that is it. So that is now my end process. That will create a 1 gigahertz square wave clock. Now I got to save this and compile it and make sure that all my colons and stuffs are in the right place, my colons and semicolons, and that appeared to work. Now let's think about this. I'm going to come along and I'm going to create a reset signal. Okay? The reset is going to do the following. We would like it to start off the simulation in reset. That means that it's going to be 0. It's in reset. That means that everybody, the D flip-flop is going to have its outputs set to their default level, and then once you release the reset, it'll start running. and it'll look for that first edge of clock. So I recommend the following. If this is going to be time equals 0, so this will be the beginning of our simulation. This is t is equal to 0. Why don't we hold it and reset for 1 full clock cycle, and then we'll take it up and leave it there for all time. That means that this right here will be the first edge of the clock that will actually be recognized. And this will allow us to test that our D flip-flop is not responding to this edge right there. If I do that, how long do I need to leave reset as a 0? 1 nanosecond. Okay? All right, so that's good. So let's see how we could do this. I'm going to come over here, and I'm going to do this as a separate process to keep it clean. So I'm going to call it reset proc process. And now what I'm going to do is I'll come down here. I'll say begin. And I'm going to say reset underscore TB gets assigned a 0. And then I'm going to wait for 1 nanosecond. And that took care of the low part. Now I'm going to take it high, reset underscore TB goes high. And now what would you like to do? I've come out of reset. Leave it forever. So how do I leave something forever? Wait. And I just say that's the end of it. This process will actually never terminate. It will suspend indefinitely for the rest of the simulation. So that if it ever terminated, what would happen is it would immediately fire again. It would immediately trigger because I don't have a sensitivity list. But I don't want that. So let's make sure that that code looks good. So now I'm going to come over here, and I'm going to say compile it up, compile selected. Everything looks green. Life is good. Now we need to put some data in here. So now what I'm going to do is I'm going to say data proc, and it's a process. And now I have to really think about what do I want to drive into this thing. Okay, so I'm going to start off and I'm driving DTB, and it's going to get some value, and I don't know what it's going to be, and then I'll wait for some value. Let's think about this. How do we want to drive this? So this is our kind of signal here, and we're going to have ourselves a data. During reset, we really don't care what it is. Okay, we really don't care what the data is. We could actually put it to don't care. You want to do that? I don't care. I honestly don't care. Neither does the data. All we need to do is make sure that at some point over here, maybe about right here, we put the data to something. So during this region right here, which is, it seems like about 1 nanosecond, we need to put it to something, and I don't really care what it is. But over here, what I'd like to do is put it to something else so that this right here will get updated. So Q will get updated. If we come out of reset and we're in a 0, then if we put a 0 right here, it'll latch in a 0. So just to make it interesting, why don't we make this a 1? And then why don't we come over to here and we'll do another nanosecond, and we'll make this a 0 so that on this edge it goes to a 0. And then let's put it back at 1 for the rest of all time. Okay? I'm kind of intrigued by putting like a don't care right here just to make sure that if it latches right here, if it sees that, if it actually tries to latch that don't care, it'll freak out and the output will go to a don't care. But it should absolutely not do that because it's in reset. So by setting up your test bench like this, you actually test all these different conditions that we actually care about. Okay? Does that feel good? Okay. Life is good. Life is good. Life's so good. It's just so good. I'm trying to get this on the document camera so that you can see it while I type, and it's like there's gravity shifting us to the left. Okay, here we go. I'm going to come down here, and I'm going to make TB. Does anybody remember what? Let's just do that one. I think that's what it is. If it's not correct, if that's not supported in standard logic, we'll know right away. How long do you want to have that there for? How long is that going to go for? 1 nanosecond. Okay, and then let's do TB gets space that out a little bit. Now we're going to go to make it a 0, and how long is that going to go? So how long is it from this moment in time right here to this moment in time? It's also 1 nanosecond. Okay, that's fine. And then What about this next one?
Aren't we making line 2 a 1?
Yes, we are. How quick was that change? So we made that a 1, and then now we're going to do this one right here. We want to make that a 0 for how long? 1 nanosecond? Okay. And then what do we want to do? D underscore TB gets assigned a 1. How long do you want to hold it at 1? Forever. All right, so at this moment in time, we'll have a compile error because we didn't type begin, but we can catch that before the compiler does. So begin. And let's just see what happens here. So I'm going to go compile, selected. Boom. This was a good exercise because it makes you think through what you're trying to do. This will become a lot more important once you start doing finite state machines. Because finite state machines, you got to not only set up the clock, set up the reset, but you got to set up a sequence of inputs to make the state machine traverse all its paths. So this was kind of a simple example of how to set up a test bench. Now the key is I have this thing and it compiles, everybody's happy. It should work, okay? The only thing I got to do though is go create my D flip-flop. So I'm going to go ahead, I already declared the ports in my test bench. This is typically how you do it. You do the test bench first, and I'm going to come over here, and I'm going to come down here and just paste my ports. You know what I get sick and tired of doing? Typing this. So I just copy and paste it. Boom. Then I come down here and I say entity DFF is, and look it, I got my port definitions. I go end, entity. Look how fast you can crank these out. That was a copy, that was a paste. Then you do architecture. I'm going to call it dflip-flop underscore TB, what? Arc of DFF is. I come down here, I say begin. Come down here, I say end architecture. And then I got to make sure I got all my semicolons in the right place. Let's compile everybody. Compile all. All that, it's time to model this. I say to you, we use a process. Now, I'm not naming this process. I don't need to name it, it's optional. But I could name it and I usually name them when I have a whole bunch of different processes in my simulation. In this one, it's kind of interesting because I have 3 different processes in my test bench. Then I have this process. So I could actually name this something descriptive. So I could call it like D flip flop to make it really obvious that this is a process. I am going to use a sensitivity list. Why? Because this is a real circuit. Okay? When we synthesize, we must put in a sensitivity list. I ask you the number 1 question, the most important concept. What is in the sensitivity list for the D flip-flop? What are the inputs that cause this thing to react?
The clock.
Absolutely the clock. We always have clock. What else? What else?
Reset.
What's that? Anybody?
Reset.
Anybody? The answer is reset. Absolutely. Because we're asynchronous to reset. And finally, is there anything else? No. But D is an input. Why are we not going to have this trigger on D? That's not what triggers a D flip-flop. It's just it is an input, but we only look at it when we get a clock. We don't even look at it when we get a reset, but we update the outputs based upon events on clock and reset. That shall never change. You shall never list anything else on the sensitivity list, no matter what you see online or no matter what anybody else tells you. This is how you do safe synchronous digital logic design. Okay? All right. You can quote me on that. Begin. I say to you, number 1, what is the first thing that we need to do? We need to take care of the reset condition. Okay? Here's the code for it, but I want to type it in for you. We always do the highest priority thing first in an if-then statement. So what we're going to do is let's look at reset. If it's asserted, we got to assign to the outputs. So I'm going to do if, and I'm going to say reset is equal to a 0, then what? Reset is reset. You've asserted the reset. What does that mean to a D flip-flop? It means Q goes to 0. That's what reset means. Q goes to 0. So I say Q gets assigned a 0. You know what else you get for free, though, in a D flip-flop? You get QN. It's just the inversion of N. No, it's the inversion of Q. So I just say Qn gets assigned a 1. And I feel so good. Now, I'm ready to model the clock. We are going to do this as an else if. And now we can do it two different ways. I can do else, if, and now I need to do rising edge of a clock. We have two ways we can do it. The first one is clock tick event. Remember a signal attribute? That means there was a transition. And as you saw that transition, clock was equal to 1. That is the agreed upon way to synthesize a rising edge triggered thing. Okay? So this will work, and we'll leave it there. What's the other way that you can do this? You have a function in the standard logic 1164 package that's called rising edge. We could replace this with rising edge, but we'll come back later. So I'm going to come back later and test that. Okay? For now, tell me what happens when I get a rising edge of a clock. What do I do?
Set Q equal to D.
I set Q is equal to D. Yes. I say Q gets D, Q naught gets not D, and then here's the main question. You have an if. You have an else if. What do you do in all other situations? Nothing. You just hold your values. The way you model nothing is to write nothing. So in this situation, we actually just end my if statement. I do not even put an else clause in here because there's nothing else I want to do. Then I end my process, and I feel like this might be good to go. That's the entire model. So look how clean that looks. Let's go ahead and fire that up, and let's see what happens. Compile selected. 2 errors. Oh boy. All right, not a big deal. Does anybody see it? Expecting then. Oh, it's a fickle little computer. So after the else if, you got to go then. No big deal. No big deal. All right, so then I'm going to go boom, compile selected, successful. Let's load this up and see if this looks even remotely close to what I was trying to get out of here. Okay, so I'm going to say let's load up the D flip-flop test bench. It all fires up. I don't see any warnings. I go ahead and let's add 2 wave signals in region. And now I got all my signals. And I want to run this for a couple clock cycles. Let's run it for 5 clock cycles. How many nanoseconds should I run my simulation for?
5.
5 nanoseconds. All right. So first of all, what's going to happen? I want to go back to this guy right here and say, what do you think should happen? What's Q going to be? Q in this situation right here should be a what? It's either going to be 0 or 1. It's going to be a 0. Why? It's because you're in reset. Once you come out of reset, it's going to hang at a 0, and it will hang as a 0 until it sees the first edge of clock. So it'll see the first edge of clock at 1.5 nanoseconds, and what should happen? It should go up to a 1, and then it should hang there until it sees the next rising edge of a clock. And if we set up our data correctly, it will do that, and then it will sit there and go back and forth, and it'll go back to a 1 for all time. All right, so here we go. Let's see what happens. So boom. Here we go. First of all, let us look at our inputs. The input is a clock. It is cruising 0, 1, 0, 1. We did it. We made a process that looked pretty good. Let's look at reset. Here's reset. It was a 0 up until a nanosecond, then it went high. Our process for reset worked. Let's look at D. Here's the input D from our test bench. It was a don't care, or a dash. Then it went high. Then it went low. Then it went high for all time. Finally, here's Q. Let's get rid of Q and Q bar. We know it's the opposite, but I just let's nuke it. Here's Q. It starts off at a 0. The first edge of clock, this is critical. It did not get updated with a don't care. Why? Because it's in reset. So that tested the first condition. That tested whether a reset worked. Now we come over, we're out of reset. We are holding at a 0 right here. And then it sees its first rising edge of clock, and it goes to a 1 because that's what D's at. It holds it until the next rising edge of a clock, and then it goes to a 0 because that's what D's at. And then it goes to the next rising edge of clock. It goes to a 1 because that's what D's at. And then from then on out, it should just go and stay there forever. And it did. Ta-da! How sweet is that? This will fully synthesize. Now, the last thing I want to say is you could come in here, and instead of doing clock tick event, you could do the function rising edge, and then give it the argument clock. she'll let you know it's me typing. Okay, rising edge of clock. And let's see if this simulates. So I'm going to compile this puppy. Compile, selected. D, successful. Now I go back to my wave. I restart it. Yes, yes. I run it. Boom. Let's do it a boom, boom, boom. Look at that. It works the exact same way. Whether or not you use rising edge is completely up to you. Another thing to keep in mind is it's only supported in the standard logic 1164 package. And that is how we've modeled now our first sequential storage device, the D flip-flop.